Hi, students. The purpose of this video is to help you understand or check for any doubts or check your work in the calorimetry lab that we did last week. Let's check the learning goal, and at the end of this lab, make sure you go back to the learning goal to make sure you achieved it. The learning goal is I can develop a model to illustrate that the release or absorption of energy from a chemical reaction system depends upon the changes in total bond energy. So at the end, just go back to this learning goal to make sure you reach the goal. Okay. You can do these predictions on your own. You can do the research of calorimetry to answer this question. I think that's easy. We're going to focus our attention now in explaining the equation for the heat of reaction. Okay, as you know, the calorimeter, we used a coffee cup calorimeter. We used 2 cups to prevent the heat from escaping. And since it's this experiment is run at atmospheric pressure and we didn't change the pressure, we can calculate the heat of reaction using this equation, where the heat lost or gained in the reaction equals the heat lost or gained by the solution. What does that mean? That if the heat was lost in the reaction, then the heat will be gained by the solution. And the opposite, if the heat was gained in the reaction, it means that heat was lost or gained in the solution. That's why we need this negative here to indicate that the heat gain would be opposite to the heat loss, as stated on this sentence right here. Okay, the M stands for the mass of the solution, and a reminder of previous knowledge. Solution means both in this case, the solute is water, plus the solvent is the water, and the solute is the salt that you're using. So the mass of the solution includes both the water plus either the sodium carbonate or the sodium bicarbonate used on these experiments. The C represents the specific heat capacity of the solution. And there are here we have a note where we're going to use the specific heat capacity of water. Why do we do this? Because in aqueous solutions, we assume that the most heat gained or lost will be the same as the one that appears on the water, the one that is shown with the water, because the salt used was a small amount compared to the amount of water. Also, in the mass of the solution, as you remember, you measure the volume of the water. So how can you get the mass of water from its volume? You use the density of water of 1 gram per milliliter. So every milliliter, you can change it to 1 gram of mass. So if you use 50 milliliters, you can change it to 50 grams of water. You add that to the amount of salt that you use, and that's your mass. Now the change of heat, you're going to do final temperature minus initial temperature. And as you notice, you could have here a negative value if the initial temperature is higher than the final. Okay, once you have the heat of reaction, you can calculate the enthalpy of reaction by just dividing the heat of reaction by the moles of the salt that you used. Okay, again, you can do this research on your own to answer this question. The procedure, it's stated here. You can read it on your own. If you were on the lab, on class last week, you can remember that you did this and the way that you did this. If you were not here, there's a link of the experiment done in class by your classmates. You can watch it as well. Now, the data table that I have here, I have these values, but I invented them. These are examples of values you should place on this chart the values that you actually collected during the lab. If you were not present, then you can use your classmates' values. Okay, so these values was for the dissolution of sodium carbonate. You were supposed to do the experiment again or share values with other groups where you do again the experiment, but now using a different salt, sodium bicarbonate. And again, these are values that I invented. You should add the ones that you collected during the lab. Okay, then we're going to go through the calculations quickly to make sure you did the correct process or to make sure you're understanding what this means. Okay, so they're asking us to calculate the heat of solution using the Q of reaction formula. They're asking you to calculate the number of moles of sodium carbonate and to calculate the enthalpy of solution per mole of sodium carbonate. So the way that this is done, okay, so the bells of the church are on the background, which is totally fine. Let's move on. So if we're using this reaction, this equation, sorry, we are going to use the mass of the solution, which I place 55. You can use the, if you did it exactly to the dot, the 50 milliliters and the 5 grams, you should have the 55. Or the actual mass that you use on the experiment, because remember that we have a range of plus minus 0.01 or zero 0.1 gram of error. So use the actual mass that you used. And also here I use 5 degrees Celsius, but you have to place the actual temperature change for the experiment that you did in class, or again, if you were absent, of your classmates' experiment. So when you multiply these values, you get a number in joules, and you should get a negative value of heat because this reaction, as you noticed, increased the temperature of water, showing an exothermic reaction. So that's why this negative is here. It means that the heat was released from the system. Then you can calculate the moles of the sodium carbonate, as we do always with stoichiometry. The grams, again, if you have a different value, place it here. And you multiply times the molar mass, which in this case is 105.99 grams. Remember that this value comes from the values of masses from the periodic table using 2 units for sodium, 1 for carbon, and 3 of oxygen. So then when you do this, when you multiply the grams by the 1 mole divided by the grams, you will get the moles of sodium carbonate. In letter C, they ask us to calculate for the heat of reaction, which is only to divide the heat of reaction by the moles. And you should get something similar to this. Don't forget your units in every step, and you have your calculations. Okay, later is asking you to represent the equation, placing the values of heat. This negative value means energy is released. What that means on a chemical equation, it means that the heat can be considered a product. That's why it's added here on the product side. Notice that the negative sign is only used for the delta H, but when you place it on the product side, you place it as a plus because the only thing that you are relating here is that it's a product because the heat is released. Notice that I removed the times moles. Why? Because I have here a subscript of 1. So it's obvious that it's 1 mole of the solid here. It represents 1 mole of the sodium carbonate. So you can just place it in joules, or you can place it by moles. Either way would be correct since it is representing 1 mole here. The delta H is negative. Again, exothermic reactions that release heat will have a negative sign. Now, this is a note that I added here. The actual value for the enthalpy of this reaction of the dissolution of sodium carbonate is negative 24.8 kilojoules per mole or negative 28,800 joules per mole. So this is the actual correct values for this reaction. You should have been able to determine the enthalpies of reaction to within 10% of the true values. And the way to calculate the percent error is as follows. The real value, the absolute value of the difference of the real value minus the actual value divided by the real value times 100%. I did the procedure here. And with the values that I invented above, I got a 1.61 error. You can do this with your own values, and if you are within 10%, if this answer right here is within 10%, you're pretty close to the actual value, so you did a great work in the lab. Congratulations. If you're off to more than 10%, then you have to think of what could have gone wrong. Like if I'm going to do this lab again, where would I be? Where would I have to be more attentive? So the possible sources of error include incomplete transfer of the liquids from the graduated cylinder to the calorimeter, if you didn't wait until all the liquid was passed from the graduated cylinder to our coffee cup. Not raising calorimeter parts between exercises. If there was a salt there of sodium carbonate and then you did the sodium bicarbonate, that could affect it as well. If your calorimeter was not dry, then you're having more water that you're not considering. Or if you didn't steer correctly, the reaction didn't went all the way to completion. Or if you stop the reaction before it goes to completion. So again, this lab was, you were supposed to do this patiently. So this is just a note of the actual values. If you were within the 10%, congratulations, you did a great job. Okay, then in number 3, it asks you to do an energy graph model. Similar to this, of course, this is not the one that you should have. You should have the reactants, so the sodium carbonate solid in here, right? And the products, which is the ions dissolving water on the side of the products in letter C. And this delta H should represent the value that you calculated from above. So make sure you make your own graph showing all the values. And remember what this is showing is that first the bonds are being broken. We're going to talk about this later. And then bonds are being formed on this side of the graph. So then I went over now the calculations for the sodium bicarbonate. I'm going to add this document so that you can access it and you can check it later with detail. So I did the calculations again, the representation again. Again, I'm showing you the actual value of the heat of dissolution of sodium bicarbonate. 16,900 joules per mole, and you can calculate your percent error and think about what could have gone wrong if you are higher than 10%. Again, I placed here a general endothermic graph. You should place your own with the proper reactants and products and with the proper enthalpy change. Then it says here in number 7, what bonds are broken in both the dissolving of the sodium carbonate and the dissolving of the sodium bicarbonate. And what you can think here is what happens to the reactants. If the reactant is a solid and the product is ions in solution, the bonds are being broken are actually the bonds of the ionic compound. So that positive sodium and that negative carbonate ions that are bonded through an ionic bond, those are the bonds being broken. the bonds of the solid, the ionic bonds of the salt. And then it says what new attractions are being formed. So here, what are being formed, remember that when a salt dissolves in water, one note here, salt is a general term for ionic solids where you have a positive ion and a negative ion. Remember that the common salt is table salt, sodium chloride, but these are also salts because they follow the general definition, which is a positive ion and a negative ion as a solid, ionic solid. Okay, so sorry. The bonds being broken are these ionic bonds that are being broken. The attractions that are formed are the positive ions are now attracted to the negative section of water. Remember which is the negative section of water? You should remember that. Remember that water, it's H2O, where the oxygen is covalently bonded to the hydrogen. So you can remember from previous knowledge how will those ions will bond with intermolecular attractions to the water, and that's what you can answer for number 8. And for number 9, you should know by now that the sodium carbonate ended up being exothermic because the energy was released, while the dissolution of sodium bicarbonate ended up being endothermic because you needed energy to break the bond, so energy needed to be absorbed from the solution. I hope this helps. I'm going to add this document for you to access it, and then now you can finish your lab. Thank you.